Okay, um, so thanks everyone for coming Friday afternoon. So we're very excited to have Chinmay Nirkhe visiting us from the University of Washington to give this special talk on a very recent paper solving a long-standing problem in quantum complexity theory about separating QMA and QCMA with respect to a classical oracle. So this is a problem that many of us in this room I think have thought about. I've simply thought about it, so it's very exciting to see this resolution. And without any further ado, I'll let Chinmay take it.
Thank you. Thank you for the invitation. It's always lovely to be here. So maybe raise of hands. Who's heard of these two complexity classes, QMA, QCMA? Okay, that'll save us a lot of time. Okay, this is great. Uh, it's glad to know that other people care about these classes past myself. So today's talk will include. I like to just show you the previews of what drawings I'm going to include. There'll be some drawings about Merlin and Arthur's. We'll talk about bosons, which will be the part which I learned the most about during this problem. And I'll hopefully leave you with some lessons and some open questions. Okay, so let's just start with a little bit of recap of there are two appropriate analogs of NP. So how should you think about NP? Many ways to think about it, but today we'll think about it in the following kind of interactive proof setting. There's an untrusted or arbitrarily powerful prover named Merlin. He sends a classical message to Arthur. Arthur, is sitting there. He's a knight. He's trying to decide some computational problem like is X in a language, and it's NP or MA if he is a classical polynomial time computer, and he just computes some function that is dependent on the question he's trying to ask, and of course, whatever message he may receive from said Merlin. Okay. First, quantumization of this is you just let Arthur be a quantum computer. However, the message that's sent to him is still classical. He still gets a classical message. And this is the class called QCMA. And if you allow the message to be quantum, the class is QMA. And the question we're going to talk about today is whether these two classes are equal or not. And what we'll do is we'll resolve that they are distinct in a query complexity model. Okay, so these are the three kind of classes you should keep in mind. And there's a containment going from left to right, with QMA being the largest one. And we're going to prove a separation between these two guys over here. Why should you care about this? Well, quantum states, they're kind of hard to describe. And just a polynomial time Arthur by himself, even if he had a local Hamiltonian system, which is, a complete problem for QMA, and he wants to understand it, assuming BQP does not equal QCMA, even if he had copies of the state psi, he wouldn't be able to write down a description of it. Now, in one world, which is a little bit happier world, Merlin is smiling, Merlin can take whatever state psi he's thinking about, and he's able to, with enough computational power, he's able to write down a description, puts it in the mail. Arthur then, in his laboratory, uses the description to verify this whatever property of the original problem, in this case, the local Hamiltonian. It's crucial that Arthur does not actually need to be able to generate the state psi himself. There could be alternative verification procedures where he's able to be convinced of the statement, that say like H has a low energy ground state without actually being able to create the state itself. Maybe there's an alternative proof that he could have read. This is one situation. However, when QCMA does not equal QMA, we're in this kind of predicament, meaning that Merlin, he's going to struggle. He's not able to write down a description of the state psi that Arthur is able to certifiably verify. He can't write down something which Arthur can trust. And moreover, he can't even write down anything that will help Arthur be convinced of whatever computational task is in front of him. And the only hope then is that Merlin sends him a copy of the state, which he can verify, but not write down a classical description of. There are many ways to think about this problem. There's ways to think about this as a boon, as a curse. A lot of cryptography is based on primitives of uncopyability or unclonability. So in that regard, these kind of things can be really a positive. Okay. So resolving QMA versus QCMA is just trying to figure out which of these two worlds do we live in. And let's just say, what can we prove? Well, unfortunately, there's this family of containment with P and P space sandwiching them, and we don't know how to resolve them. So like, sort of, really miraculous work, we're kind of stuck in the best thing we could do is say prove it what's called an oracle separation. So an oracle separation is a world in which both Merlin and Arthur have access to some black box object, uh, which when we say black box object, we just mean that they have only input-output access to this object. And in this sort of slightly tilted world, where this black box object exists, we can try to prove separation. This is tantamount to a query complexity bound, if that's a more familiar way of phrasing it. In the world of quantum problems, there's not just one type of black box object, there are many. And one of the things that is very common is what's called a quantum oracle, which is just a family of unitaries, one for every size, that can either be applied or controlled applied. A simpler oracle, which means a stronger separation, it could be a classical oracle, which has access to a generic binary function given by O. And this function, what can you do with it? You can evaluate it at any input x of any length, and no other information is provided by an input other than the output. So you query it at x, all you'll learn is the output of O at x, nothing more, nothing less. Yeah, Vinod?
Between NP and TCMA,
Yeah.
separation?
Yes. I mean,
Separation.
oh yeah, just because anything that even separates BQP and NP would work just as fine. Yeah, you can hark on the quantum side to get there. So what we're going to do today is we're going to prove that with respect to some classical oracle, these classes are separate. So brief history, I won't go through it, but these are just some of the papers. What basically happened was people started working on this problem. We started progressively as a community chipping away at the oracle, removing sort of the quantumness until we got to our final work today, which is about something called spectral correlation, which we'll describe in.
So just to understand, yes. Classical oracle, you can still access it in superposition and get.
Yes. Yeah, you can access it in superposition. It's just you can only get the input output. So you don't get to learn like whatever circuitry is required to, instantiate the function. Okay, so maybe why should you expect them to be separate? The intuition comes from the fact that random quantum states are hard to describe. They just take a really large description classically. This is true for a random state. And if you could create some oracle problem, which requires that the verifier at some point in his computation, his computer must hold on it some particular quantum state. And this state psi was one of those special states which you knew the hardness of, then you couldn't get polynomial time classical witnesses because run the classical witness, stop the algorithm at that point, you have hard state, which you couldn't have gotten. So intuitively, this is why you believe this to be the case. And this was exactly the technique that was used by Ernst Kupperberg, which was the first quantum oracle separation between these, is to just say, look, at some point your computation has to hold a really complicated state, ergo it cannot have a classical description. What's challenging about this? What makes this really hard? I'll say this, that it's relatively easy to create a computational task, an oracle task, with a QCMA lower bound. Unfortunately, most of our lower bounding techniques simultaneously will also prove a QMA lower bound. Our proof techniques for non-deterministic quantum lower bounds are sort of agnostic to whether the witness is classical or quantum. So you create an oracle separation that just knocks you straight out. It's QCMA can't solve it, and neither can QMA. It's kind of problematic. A great example of this is set size estimation. If you give me an oracle, which either is a set of, say, size square root n or n to the 1/3, okay, out of a universe of n, and you ask me to estimate size, you can't do this in BQP, you can't do this in QCMA, but you can't do it in QMA either. So you're kind of stuck that where is the problem you can find which separates these two? And set size estimation, the sort of the way people have thought about this is you say, okay, well, imagine I gave you a little bit more. I gave you a second oracle, which helped the QMA guy solve set size estimation. I had an earlier work with Anand where we did this with an expander graph. There was some other work that did all sorts of other things, and we'll see in today's work how the second oracle fits in. But then the challenge, of course, is to argue that whatever second oracle you have now provided is not helpful. The second oracle, like with classical witness is kind of junk, right? It's junk to the eye of a polynomial time algorithm, at least. And what we'll do today is we're going to prove this using some nice bosonic kind of perspective, which will be this really kind of interesting thing. At least I feel is new, if there are any physicists who are just like, oh, this is so obvious, apologies. I just learned about this like 3 months ago. Okay. So how are we going to do this? Well, let's just get started with the proof because we don't have insane amount of time. What we're going to do is we're going to talk about property testing. So property testing is the following. You're going to fix a size parameter n, and we'll say a property testing problem about a pair of oracles. We'll call the oracles today, and for the rest of the talk, there'll be two of them. One's called S, one's called U. Okay. And we'll say that the property testing has a quantum polytime witness if the verification algorithm V can make controlled queries to both S and U in superposition. So it's allowed to, ask some superpositional query to S, some superpositional query to U. It could even ask simultaneously to S and U. That's not that important, but you can let yourself as much time of this as you want. And what's known is you have just the completeness, soundness kind of parameters that you might expect, which is for all the yes instances, a bona fide honest witness is providable, which is accepted. And for all the no instances, no matter how nefarious the state you try to produce, I will reject it with very good probability. 1/3, 2/3, just arbitrary constants. That's not important. Okay. So this is like a quantum property testing with quantum witness. You can flip this and just talk about classical witness. Same thing, just well-defined. What I won't say today is this part. This is a diagonalization argument that says as long as you have a property testing problem which you can generate for all sufficiently large n, you can lift this to be the oracle separation. If you want to read this, the standard diagonalization trick, it was probably on your complexity theory final, but it's worth working out if you haven't seen it before. Okay, so we're gonna just do the property testing problem. So what is the oracle? The oracle is the following. It's called spectral correlation. It comes from the name comes from estimating the spectral norm of a correlation matrix. And there's a nice picture associated with it. So it's an oracle about two sets, SU, which you can think of as subsets of 0, 1 to the n. You can also think of these sets according to their membership function. So a membership function is just a map from the set to 0, 1, just, indicating membership or not. So you can think of S and U by membership functions, or you can think of them as sets. It's not going to play a role. For the pictures, it's nicer to think of them as sets. Okay. So the subsets S and U are spectrally correlated if there exists a state psi such that this particular quantity is at least alpha. Okay, what is this quantity? It says take psi, first measure it, and make sure it's only supported on the strings from set S, then apply the Hadamard transform and make sure it's only supported on strings from U, or at least alpha supported on the strings from U with respect to the probability. So the picture you should have is, has anyone seen the cover of Gödel Escher Bach? Where there's the GEB and that shines the lights, the different shadows from different angles. This is my attempt at that, right? It's sort of that the state psi, it has two different shadows, i.e. distributions it generates, one in the standard basis and one in the Hadamard basis. And the idea is that, roughly speaking, for large enough alpha, what this means is that psi, its shadow, when you cast its standard basis, is mostly supported on S, and psi's Hadamard shadow is mostly supported on U. Right? S and U are just deterministic sets. You just take these shadows and you want to just calculate the whole sum. Yeah.
So S in the subspace and U its dual, this is perfect. Right?
Yes. If S was a subspace, U was its dual, yeah, you could get exactly, spectral correlation exactly 1. And in fact, the Aronson-Cristiano result from way back when even has a two couple line proof that if S is a subspace, U is its dual, that this number, this pi U H pi S actually just is equivalent to the projector onto the state. It is exactly the projector. And that's a great point because in a little bit we'll see it's kind of similar enough here today. Okay. Everyone okay with what is spectral correlation? Okay. So this is just a property of two sets. So what's the computational question? Computational question is you just give me two parameters, alpha, beta, and you just want to know whether S and U are at least alpha spectrally correlated or at most beta spectrally correlated, is with this like promise that it's one of the two scenarios, right? So this is just like the decision version of estimating spectral correlation to an accuracy given by alpha beta. And today, alpha beta will actually just be constants. They'll be 59% and 57, sort of whatever, doesn't really matter. So the constant is what's more important. Okay, this problem is in QMA. This will be the only time we really talk about QMA because really the QCMA lower bound is the more interesting side. What's the verification? You just send me the state side. You look at the state side, you use one oracle to measure and check that you are supported only on S, reject if you're not. If you are, Hadamard transform, measure again, is exactly this. I mean, this is just mathematically the success probability of this test is literally the spectral correlation. And so if you give me if someone sends you over the state that maximizes the eigenvalue of this, this correlation matrix, then you're just going to succeed with that much probability. So the problem is nicely in QMA. Okay, so how are we going to prove it's not in QCMA? Well, we need something that's going to distinguish our classical and quantum witnesses, right? Because like I said before, the real challenge is we need some technique where my lower bound technique cannot simultaneously prove a QMA lower bound, right? Because then something would be going wrong because I just showed you the problems in QMA. So what's going to happen? Well, let's just say what makes them different. And here's the simple idea. This was originally in a partial work by my co-author, Mark Zandri, towards this result. It's called Towards QMA QCMA Separation. But he remarked, and this is, I think, really, the most powerful idea here, is that quantum witnesses, they're these use once objects, whereas classical witnesses can be reused. I mean that in the following technical sense. Sorry, some of the slides are handwritten, but if my handwriting is bad, please just let me know. Okay, what is it? You give me a witness psi in a quantum circuit V, you get one sample from apply V to psi and measure. You get one sample, easy enough. How do you get a second sample? I don't know. You would need to know something about psi in order to get a second sample. Whereas if you give me a quantum witness W, I'll print you as many samples as you like. It'll just take me some time, run V each time. But that's because I can clone the witness W, but I cannot clone psi. So somehow, paradoxically, a classical witness is more powerful in this one kind of funny way than a quantum witness because it's clonable, right? But what we're going to show is that this is just like it's too powerful. It's so powerful that we're going to prove a contradiction, right? It's just too good to be true, and that's going to be our proof. And luckily, just because because our proof is going to hark on being able to generate many samples, we won't. The same argument doesn't hold for QMA, so that's good because that would just mean something is wrong. Okay, how am I doing? How's everyone feeling? Thumbs up. Everyone kind of
Are
understands.
you going to try and contradict with this?
Yeah, we'll get there in 1 second. I think it's here we go. Next slide. Okay. So Ankur asked, what's the contradiction? So this slide I'm going to spend about 3 minutes on. This is going to be very important. So you're going to have to bear with me for a second. So we're going to prove I'm going to put 3 theorems on this slide. If you prove all 3, the result will just follow very quickly. Okay. Here's the first theorem. It's kind of a weird theorem. It says for any V that's positive, and any quantum query algorithm that makes only T queries to just U, you can guess V points in S with probability given by this number over the algorithm and the randomness in sampling SU from some distribution. Okay, that's a complete mouthful. We're going to break it down. Okay, so what's going on? I'm going to write down some distribution, which I'm going to call strong. This distribution is going to be supported basically only on spectrally correlated instances. Okay, so these are going to be S's and U's, which are at least, say, 59% spectrally correlated. Okay, and then the algorithm is going to only make T queries to U and guesses V points in S with some probability. Seems confusing? Let's look at the picture. The picture helps, I promise. My algorithm is Arthur. And what does Arthur do? Arthur is a knight, but he will look straight at you Okay, he only looks forward at you, and he has to like drop pins on the ground, and those pins better land in S. Okay, and we're trying to put a bound on the success probability of this algorithm. Okay, I claim this theorem is true, that I can prove such a bound. That basically, and Arthur, who only there's no witness, there's nothing, it's just a query algorithm. Query algorithm where you only get to look at you, and the number of queries you make is T. Your success probability of dropping V pins and having all V pins land on S is given by this. This number is really small, first of all. As long as V and T are polynomial, this thing is like this is exponentially small inside the exponent, and it's being raised to V. A couple ways to think about this. One way to think about it is saying the first point you guess, very unlikely to be true. Think about what happens when V equals 1. But it says, even if you got the first point, imagine Arthur drops the pin and all he realizes is it landed successfully, game's not over. His second guess is also really unlikely. And he keeps going unlikely, unlikely, unlikely. And that's the success probability. Just that anyone who looks just at you is really bad at this game. Okay? When in doubt, you just got to remember this. Okay. You say, why on earth think about this particular problem? Like, where does this algorithm come in? Here's theorem 2. Theorem 2.
Sorry again, but this is over S and U that comes from some distribution
From
over
this-
correlation. over
Yeah,
the
some
correlation.
distribution that's very over correlated instances.
So what does it mean that the quantum query algorithm makes T of n queries to you?
It gets to make T queries in superposition that only access U. So it's just any algorithm where you could write it out with the gates to the U that you can run in superposition that just at most T of them in the circuit.
So it can make a superposition of as many things as it wants.
Yes, it could ask for a superposition over all points in U, whatever half it wants, no matter what it does. It's just anything that it only has to make T of them. It could make them in parallel. It could make them in series. It could depend on the answers to the first queries. Anything you want. It's just at the end of the day, he makes T queries and then he gets to drop his pins. And we're just estimating his Arthur's success probability. We're saying it's bounded by this number.
And during this procedure, he has no query access to S.
He never gets to query S. He never looks down. He just has to look straight at you and drop the pins. Okay, where does this come from? Why think about this kind of funky model? This is theorem 2. Theorem 2 says, if there was a QCMA algorithm, then for a type of yes instance, which we'll have to call a strong yes instance, but for now, ignore that word. It just says for such strong yes instances, there exists a sampler algorithm which only makes V times T queries to U, but produces V distinct points with a lower bound on the probability. So theorem 1's an upper bound on the success probability of a task, and theorem 2 says for strong instances, you have a probability lower bound. And we're going to build this from the fact that there exists a QCMA algorithm. By the way, both of these problems, we've taken something about QCMA, we've built a sampler lower bound. The sampler, this guy, there's no witness here, there's no Merlin, nothing. It's just Arthur all on his own. We're just saying, if this was the case, I can produce this lower bound. And this lower bound is a situation of this type, where Arthur only looks at you and drops pins. Okay? If you ever give him a strong yes instance, and there exists a QCMA algorithm for spectral correlation, he gets this lower bound. Let's break down this lower bound. This lower bound is saying something of the following nature. It's saying, look, you pay a penalty of 2 to the negative q in the probability, irrespective of whatever v is. I don't care about that. But every consecutive point, the loss in the probability is not that much. It's only 1 over poly. Whereas in the previous statement, the loss per guess in your success probability, like your multiplicative loss, was exponential, right? So here, the loss is only polynomial. Here it's exponential. So
does theorem 2 use the reuse of the classical oracle? Or how should I think of the classical oracle statement you made on the previous slide?
Yes, yeah, it does. It reuses it. And what's going to happen is the witness, the Q-length witness is roughly the 2 to the negative q is just going to come from someone just guessing the witness, which you could just guess a random thing and you'd get lucky with something.
Yeah, but then you can sort of repeat it without sort of paying
Exactly.
this. I don't know where U is and sort of dropping things right.
It's like is it minus you don't pay 2 to the minus q times b.
Exactly. You pay it for one-time cost you pay of 2 to the minus q, and then all previous points are there. Another thing,
The result you want. These two theorems give you the
yeah,
result.
plus lemma 3 would just says you have this distribution, which is almost entirely supported on strong instances. Like this is like you need to. This one's about a particular distribution strong. This is for any strong instance, and then this is I have to create a distribution, which is so I'll describe what a strong yes instance is in a second. But once you have that, then you have the theorem. And so I think Yael and has already seen this, which is there'll be a contradiction once you ask me to produce like 1,000 times Q points, right? What's going to happen is basically this one's saying that your exponential loss per guess, and this one is saying that you have a huge exponential cost in the beginning, but afterwards you're good. Another way of saying this is like if there exists a QCMA algorithm, you're very unlikely to get the first few points, but if you got the first few points, right, then you can just start minting points all on your own. Okay. So this is the theorem. So we take this idea that if there was a QCMA algorithm, you have this kind of funky problem about Arthur who looks at you and drops pins, and you can prove a lower bound. But then we also show in theorem 1 that that's too good to be true. And together, once you have these, 3 theorems, you have a proof. Okay. Yes.
What is the purpose of almost entirely? Like, do you need this to be efficiently separable or something?
Here?
Yeah.
No, even if this had been like half supported on it, it doesn't really matter. It just happens to be very supported. You need a distribution of instances to make some argument because we're trying to make a sampler argument about something, but if I only had one problem in front of me, then it could just have it hard coded. These are like these results are true even for non-uniform objects. So.
I see. But once you have a distribution that's almost entirely supported, like can't you pass to something that's literally entirely supported?
Sure.
Okay.
It's not a big deal. Yeah.
Yeah. Well, yeah. Why? I want to ask a similar question. What's the point of why does S need to be? Why is the size of S being 2 to the n over 10? Is that like? Why is that important to get our? Because at the end of the day, you want to get a contradiction.
Yeah.
Why is this important to get a contradiction?
It's not. Let's just note that if S was really small, or sorry, if S was really big, then it would actually be easy to guess, right? If the size of S fractionally, so this is here S is exponentially small. It's very unlikely if you just dropped a pin without even looking, your probability is like 2 to the 0.9n, right? Very unlucky. If I had proven this for a big S, that would have been a problem, right? If S was like 80% of the points, then you'd have 80% chance on every drop, okay? And then these would be meaningless.
Your theorem 1 wouldn't be false.
Yeah.
Theorem 1 would be false. It's not a problem with lemma 3, but it's a problem with them all being true simultaneously.
I guess I'm just saying I prove it for the parameter that S is this big. Yeah, it's not really that.
Doesn't matter long as it's not.
Okay, so if everyone's happy here, this is a great point. Like we can also if you saw this and you're like, okay, what's going on? This is a great point. Now, roughly in terms of number of pages in the proof, theorem 1 is 50 pages, and both of these are 4 pages each. So this is actually take the lion's work of us to prove. But I think maybe for intuition, these are more exciting and understanding. So we'll talk about these, and then we'll talk about theorem 1 for the rest of the thing, and then we'll also do it in the long talk version. Yeah, question?
Oh, it's just like the sneaky thing where you kind of delete the queries to S happening in theorem 2, right?
Yes, yeah. And so we'll see them in order. We'll see 2, 3, 1 is how we're going to prove this. Okay. Any more questions?
Size of U, you don't have any arguments.
No, U is actually going to be at least 60% of the total size or something like this. It's going to be very big. Most points. Yeah.
One question. It's kind of interesting. You never have to say anything about no instances in these statements, right?
Okay, so great. Oh my God. But he's also read the paper, so it's
I read 10 pages.
Half point. Okay. So where are the no instances coming? They're coming in the notion of strong yes instance. We'll see that in 1 second. So it has to be a notion of no instances, because if I'm going to say anything about the behavior of an algorithm, the only thing I have to characterize it is that it's like it does one thing for yes instances with another thing for no instances. So somewhere where are the no instances is a great question, and they are secretly packed into the notion of strength. So when I say something is a strong yes instance, it's packed into that. Okay, so we'll do that in a second. So let's prove this theorem. This theorem too.
Sorry, so first, I mean, for theorem one, I mean, for theorem two, I feel like you gave some intuition already, but for theorem one, you give us some intuition.
So we're going to try to study the success probability of an algorithm over an entire distribution, the distribution that's this bold strong. Okay. So what I'm going to do is I'm going to run the algorithm on this distribution, whatever candidate algorithm exists, on the purification of the distribution strong. This is a standard idea from quantum complexity theory, which is if I want to analyze the behavior of an algorithm over a distribution, and I want to kind of put together the success probability of the algorithm, combine it with the with the distribution itself, I'm just going to run it in superposition over the distribution. And the idea is going to be that when I run it in the superposition over the distribution, I can do some really nice things, which is I can analyze it in the Fourier basis, in the Hadamard basis. And this analysis in the Hadamard basis is going to have this very convenient representation in terms of bosons. And then we're going to do some math about that. And we're going to show that there is no success probability. We'll get to it, I promise.
I used to be able to like theorem one, like people have shown just with the Grover problem, like there are known results to this type. Like if you want to get instead of one marked item, you want to get T marked items, this is probably the case exponentially. This is like a much fancier version of that type of boundary.
Okay.
So this is where S is random. And there's
So our Anand brings up another point, which is the theorem one is about looking at you and dropping pins. Imagine another guy who only looks down, does not look at you, and only has to drop pins. He's also really unlikely at this, just because S is reached. But the idea is that looking at you, which is spectrally correlated with S, should not help. Okay, well, let's prove theorem one, theorem two, because we need to talk about what are strong instances and such things.
sorry, but if guy looks down, then if the first pin lands well,
Yeah.
then he knows or not.
He knows 1 point.
But then he can repeat. So you
Oh,
don't have to-
Yes, there's a key word here, which is that he has to make distinct points. It says all these problems, all of these things are about distinct points.
Like you should have a distinctive theorem one.
Oh, do I not? Okay, yeah, so he can get B distinct points. Apologies. Yeah, it's about distinct. Okay. All right, so let's prove this theorem. So what we need a notion of strength. Strength is just a word I made up. It's not, I don't know if it's convention, but a strong yes instance is the following. It's any pair SU says that S and U are spectrally correlated. It's a yes instance. But for any subset delta of S, where delta is smaller than S by some hundredth, okay, it's a no instance. Okay? So the picture is the following. Within the region S, there's like a tiny region delta. It's much, much smaller. But this U and this delta together are not spectrally correlated. Okay? So here are the no instances hiding. Okay, and this theorem, to be a strong yes instance, it has to be true for all deltas that are less than 100 of the size. Okay, and no matter what delta you give me, it has to be true for all of them. Okay, so a strong yes instance is like a yes instance whose children sub-instances are all no instances for all small enough delta. Okay, everyone good with that? Okay, so how do we use strong yes instances to build a sampler? Okay, let's do it. Let's assume there's a QCMA sampler for some length Q witness T query, okay? And let's consider its behavior on a strong instance. We'll write the algorithm down as an alternation of queries of gates U and S queries. And what I'm going to do here is just for notation's sake, I'm going to pack those U queries into the V's. Okay, so here the way I've written it out has only highlighted the S queries. There are U queries. They're just packed into the unitary V for now. Okay, so U queries have been packed in there. And we're going to write it down this way.
So in other words, you're saying you could be given explicitly and you don't care.
Not for this part. Yeah. Okay, here's what we're going to do. This is the algorithm. I just rewrote it. And this is the algorithm run on a yes instance, right? Because it's a strong yes instance, which is a type of yes instance. And I'm going to write down a sequence of states where I'm going to replace the oracles to S with identities. Okay, I'll just do this. I, iterate this kind of cascade. And this final state, which I put identities, I claim is the following. It's running the algorithm on taking S as the empty set and U as this. This is because what I'm doing here is I'm considering like, I can consider these kind of phase kickback oracle queries to S and U. This is like I didn't write this out explicitly. But when you consider these phase kickback, if your oracle is replaced with identity, it's like querying on the empty set. But what is this? This is a no instance, right? Because it's a strong property. So if it's a no instance, I have the following: that the top state I'm accepting with 2/3 probability, bottom state I'm accepting with the most 1/3 probability. So the distance between them is large. It's at least 1/3, right? Okay, then what did I do here in the middle? Those of you probably in cryptography have seen this 100 times. This is a hybrid argument, right? It tells me that for some j in this like list of t states, there was a pair of consecutive states where the distance between the pair was 1/3t, just a triangle inequality argument. But now I have this pair where the distance between them is 1/3t. So I can write it this way. I can subtract them and use the fact that everything is unitary, simplifies it. But oracle minus identity just becomes a projector onto the set S. So this says, look, if I ran this circuit, which has no query gates to S at all, only looks at U, right? Because the U gates are like snuck into the S, snuck into the V. And I measure the success probability of finding a point will be like 1/36t squared, right? This is because the norm, is 1/6t. So the square, which is the success probability, is 1/36t squared. Okay. So this yields a sampling algorithm, which only queries U, gets 1 point with probability 1/36t squared. What is it? Just pick a random j, run the computation with no queries to S, and then measure. It'll give you a point. Okay, you get 1 point. How do I get a second point? Okay, get my second point, I'm going to repeat. Here's how I'm going to repeat though. I'm going to do the exact same thing I did in the previous slide, except now I'm not putting identity. I'm going to put I'm going to simulate the oracle, which only has delta. Here, in this case, delta is just x1. So basically, I manufacture my own oracle, which only answers on x1. The same argument will work, but now I'm going to find a point in the symmetric difference of S and x1, which will, with some success probability of 1/36t squared, I'll find a point x2. Okay, I'm going to go a little fast. But in general, as long as you have any set delta that's small enough so that, it's still a strong instance, you can apply this. You just pick a random j, you run it, you measure query register, you get a point. So what you can do is you can produce sort of a cumulative sampler this way. This cumulative sampler still takes in a witness, okay? But it just each time guesses, tries to find a point, goes through. And the lemma you prove is that every sample has the probability it's going to be in the set S is, this 1/t squared conditioned on the prior samples. Okay. Just multiply, and you'll get that all V samples are 1/36 t squared to the V, right? So what's left?
You make use of the strong
Yeah.
property, but pretty weak use of the strong.
I made a weak use of the strong property. I agree. Yeah, I probably could have done with something easier.
Guess the witness or something, right?
Guess the witness. But you do it once. You just guess it at the very top. You don't guess it within the iteration. You guess it in the beginning. So you only pay the 2 to the negative q factor exactly once. And then both of these things change, but then you get this 2 to the negative q. Okay, 1 out of 3 theorems down. We're making good progress. Okay, theorem, this one's done. Let's go to this lemma. We'll have to actually say what the distribution strong is. The only reason I'm going to say what this lemma is, because that will play a role in the last part. Okay, so there's a distribution which is supported. Here's how you build it. You build it pictorially, it's really nice. You pick a uniformly random multi-set S of size, whatever, 2 to the n of 10. It's not really important. You pick it this way. Okay, it's a multi-set, but the size is so small that chance of collisions is very unlikely, but the multi-set will be helpful for the other theorem, the theorem we haven't talked about, so we'll call it a multi-set for now.
And Xi, should I think about it as uniformly distributed on uniform on X?
Yeah. I'm just going to go up. I'm going to take the S, I'm just going to pick a random state. Could have picked any of the states, but it suffices to pick uniform superposition. So I go this way. And what do I do next? I compute sort of this success probability. Like if I had taken uniform superposition and I had measured it in the Hadamard basis, I would have gotten out a point y with this probability, and I'll compute this gamma parameter, which is roughly like it's like a scaled version of the probability that you would have measured y. And but this is a number in 0 to L, where L is the size of S that I'm assigning to every point here. I need to convert this from this parameter between 0 and L into a actual. By the way, roughly these guys here, they're distributed kind of like squares of Gaussians. So they have tails, but they're mostly like small. So what I'll do is I'll just do the following: is I'll include I'll just do this. Like I'll take this and I'll just randomly subsample IID, and I'll include every y be included in U with like some exponential. The exponential thing is really kind of gross. Like if this looks gross, I know, and I don't like it myself, but it's kind of necessary to convert this number to a probability. So if you're dissuaded by this, just think of the first order Taylor of this, which is something like half plus gamma over 20, right? So
if I just kind of thresholded on gamma y, that wouldn't work. Is that right?
it doesn't work, but it's going to take us some time to explain why it doesn't work.
Because that would give me a single u
Yeah.
or s, and that should.
It should, I still believe there would be spectrally correlated, but I don't know how to prove the lower bound on the probability. Like for the lower bound, I actually really needed this exponential. We tried for
So this is for theorem 1.
Yeah.
Kind of thing, right?
Yeah.
So, maybe I don't understand bosons, but I hope I'll understand a bit more. But you can probably give us some intuition already at this point. Like it would seem that S is really big in that set. And sort of, I kind of expect U to almost look like a point process in some way. And I'm kind of hoping that, different S's induce things that are like hard to tell apart from Corey's to it.
Absolutely. Like for intuition, the names S and U,
Yeah.
that we chose the names. S kind of is the sparse of the two oracles, and U is kind of the uniform of the oracle. It's not actually uniform. It's actually very far from uniform, even or randomized over this. But the idea is that like an algorithm isn't really able to tell it apart from uniform.
Right. But so, for example, for Vinod's question, like, if you thresholded this deterministically, let's say, to construct U,
Yeah.
you have the property that you tell me S, it, determines U.
Mhm.
Now, probably the correlation isn't going to change too much, but now the way that I'm going to hide statistically, like what's happening in S so that I can't drop pins, seems dramatically harder to prove because, there's a lot more ambiguity. Like I query something, I kind of don't know what.
Yeah. I think these kind of ways of generating this distribution, like the previous theorem was just about strong distributions. I need a way of creating a distribution of things. But the problem is that I will need to create a distribution that I can later on prove the matching probability upper bound for. And the rough idea is that exponential functions, I can at least do some notion of polynomial approximations, and I'll actually use these flat polynomials that Ankur co-developed for this exponential. And I just don't know how to do such flat polynomial approximations for threshold functions and stuff. And this will yield a lot of like grossness, but we can talk more about that later. Keeping an eye on the clock. Okay, so there's a rough idea about like how you prove this. It's like a matrix kind of concentration. What you roughly show is that if you actually did this procedure of sampling, you can write this matrix M down, which is really like, the matrix that you're measuring the top eigenvalue of. And this matrix kind of concentrates around, it's like basically a projector onto S plus some identity fluff. Okay. And then you show that for any small thing, that matrix is going to be bounded away. Like I'm just going to, let's go on to more fun things. Okay. This is a kind of rough idea what's going on here. So let's do the real theorem. Okay. So now we want to prove this lower bound. Okay, and we're going to do the procedure that I suggested, which is that we want to prove this lower bound of like exponentially small per query, which roughly equates to the jth measurement needs to succeed with a very small probability conditioned on the prior j minus 1 measurements. Okay, here's the central problem though, is that this is a bound about what's the behavior on the next measurement conditioned on the previous. Except every measurement before it was super unlikely. And what's the problem about unlikely measurements in quantum computation is that they're very perturbative, right? A measurement which succeeds with probability near 1, it's like doesn't really move the state at all. But when the measurements are very unlikely, they're moving things a lot. So this is incredibly perturbative, and this is kind of problematic. But and you might say, okay, well, if you got at least some bound, could you do some approximation? But the problem is that you're going to do this so many times for v. Like, remember, the number we're trying to come up with, this is like a doubly exponentially small number, right? It's really, really tiny. It's like 1 over 2 to the n, right? This is the tiniest number. And what you have here is we're going to need a very good notion of approximation. And that's actually exactly what we'll do, is we're going to identify some invariant, which we'll show is maintained exponentially, doubly exponentially likely. And we're going to prove a probability bound given this invariant. We're going to show there's some space that, that we satisfy, and we'll do this.
So this is an invariant of the state after post-selection is the part.
Yeah, it's like after I do a query, I don't really leave some space.
Okay.
And then I'll prove a lower bound for any state that.
So some parts of the state may change dramatically, but maybe there's some core that.
There's some core that doesn't really change. That's the whole idea. Okay. So how am I going to prove this? So here's what it looks like. So without loss of generality, I'm just going to assume that I make T queries and output V distinct guesses. I can imagine my circuit looks like this, right? Just for a cartoon. And here's the best part, right? Is that because we did this whole thing, the state right here, right before guesses, is only a function of U. It only depends on U. Then the guess part is the only thing that depends on S. But because the win condition of the game is sort of dependent on S, I need to keep track of both the S and U throughout the thing. Like, I couldn't just talk about one without the other. So we'll need to keep track of both of them to analyze the success over the outcome. So what we'll do is, this is a general idea, query complexity, is what we'll do is we'll just run the problem in superposition over the entire distribution. Okay? So we'll consider this situation where every time I make an oracle query to U, I sort of have an imaginary extra register which writes out all of U. Okay? And I think of the oracle, this like phase kickback oracle, as a function that takes on the input where it's actually behaving, the long written out form of U, and does the kickback. Okay? So what you could do is you could run the algorithm on the superposition over all S and U sampled from strong. So I pick my S and U, I normalize it by the probability that the strong distribution would have outputted it, right? And I run the algorithm with respect to that. This final state is like running it in superposition on all of them. And what that tells me is that if I put that state over here, right, I run it on input of that state. So like here's the S and U, like I've pulled out those wires, right? And I run this. And now every time I make a query, it depends on what the value of U is written out. So it's like a controlled kind of query. That the success probability of this measurement, like the probability all of these measurements output, yeah, you got a point in S, yeah, you got a point in S, etc. That number is the total bound. So what I've really done now is I've said, look, the last thing we need to do for the proof is we just got to compute what this number is. This is a number, right? For a particular algorithm, this is a number, right? Just some success probability. So I've put in the strong distribution. I just need a bound on this particular number. Everyone okay with that? Okay. A lot of words. I think I just said all of them. And now here's the fun part, is we need to talk about the distribution strong. We need to somehow analyze what's going on. And I claimed that we're going to do all this in the Fourier picture. And so here's strong rewritten as how you sample it. You sample a uniformly random multiset S of size L. And for each Y, you calculate this gamma this number, and you add Y to it with probability corresponding to gamma. Okay? What we'll do is we'll first focus on purifying the choice of S. This will be where the bosons come in, and probably, the most exciting thing. And then we'll take a break, and I'll do more slides, and if anyone wants to leave, etc. Okay, so how do you purify a random multiset? This is actually something that people do in physics all the time. It has a notion, it's called bosons. Here's what it is. So how do you sample a uniformly random multiset? What is a multiset? Multiset is just a fancy way of saying a set where you can have the same element in it multiple
I'm
times.
sorry. So what does purifying mean here? I don't know.
Okay.
Okay.
So purifying is just you have a distribution.
Uh-huh.
A distribution is a vector, which is L1 normalized, right? But if I took square root of each of those probabilities, that would be a vector that's L2 normalized.
Sure.
Right? And now I can sort of consider the quantum state, which is correspondingly has those amplitudes.
Sure.
It's going to be this. So if you then just did measurements of that state, you would exactly get at those
Sampling the distribution.
you would be sampling from the distribution. The only catch is that now, by doing this purification, at least I can do some analysis, like I could apply a unitary to the state, etc. Because unitaries are
So purification
So
means
what-
generating the state? Is
Yeah,
that what you-
purification is something that takes a distribution and produces the quantum state that
That's
you can
exactly.
measure.
Yeah, except for most distributions, there are many quantum states that give you that.
yes, yeah. So I need a purification.
Doing a particular one, are you doing a random one?
I need a particular one which will be good enough for me to prove my bounds. Like this is sort of the art in these query complexity things is finding the right purification.
So you
We-
need a particular purification.
Yeah, and we bashed our heads on it for a really long time. The one corresponding to these bosons seemed like the right one in the end. At least the only one we were right proof for. Okay,
And you're purifying the choice of the set U.
and S. We'll also have to do S.
That's fine.
But for now, what we're doing is just the S part.
Uh-huh.
Ignore the U for a second. Just focus on purifying
Okay.
the choice.
And so, pardon the ignorance. So the point is, like, you want to purify the distribute. I mean, the process is well defined, and
Yeah.
the theorem holds for that process.
Yeah, it would have.
But now this is a proof technique that you want to embed it as a quantum state, such that you can interpret
Indeed.
things as some.
Indeed. What we'll see is like something really beautiful about position and momentum in queries. So give me a little bit, but let's just say what is this boson thing? So if I want to sample a random multi-set, it's like one way to think about it is I put 2 to the n balls bins in front of me. I toss the balls, but I toss the ball independent of where I tossed the previous balls. That's a multi-set. Okay, this is exactly what physicists call bosons, in the sense that just as qubits are like the superpositional analog of bits, bosons are the purifications of the balls and bins problem. So one way to write this is to say bosons is just a Hilbert space. It's just an inner product space. There's an orthonormal basis. What is the orthonormal basis? The basis is indexed by ball bin configurations. For every possible ball bin configuration, I have a basis vector. Okay, so ball bin configuration, orthonormal basis vector. It's only the same vector. It's the exact same ball bin configuration. So, I can draw them in pictures, but I can also just write out the numbers, like how many how many balls are in each bin, and that gives me this orthonormal vector. Okay. This has a name. It's called the position fault basis. What's really nice, though, is that, and a lot of physicists found this out, that there's a convenient there's a convenient second form with which you can define these bosons. These are what are called annihilation and creation operators. So what you do is you define an operator. This one's the annihilation operator. This one's the creation operator. And what they do is the annihilation operator, as the name suggests, annihilates a boson at that particular location. So this is for bin 2, right? So bin 0, 1, 2. Look, it annihilates a boson. I'm down to 2 here. The creation operator, on the same bin, creates a boson up here. I'm going to write these as proportional because they actually are not unitary. So, but just for now, let's write it this way. Okay.
So you said at some point, so the size of S is like 2 to the n by 10.
Mhm.
So you will never get a repetition.
You'll never get a repetition. It's exponentially unlikely, right?
So it's not close enough.
It's not, because I need to be doubly exponentially accurate here. I gotta be super precise because these theorems, they're only the contradictions occur at like the doubly exponentially small probability regime. So it would be lovely to just talk about multi-sets and say they're sets. Can't do that. Also, it would be helpful to not do that, actually, for other reasons.
So you could ask for versions of your lemmas and theorems where U is not taken, repetition is not a multi-set, or
Sure, you could have done this.
and the proofs would break down, or because of the
I don't know how to write these proofs in other settings. Like, it's kind of hard to prove these probability sampling upper bounds.
I see.
Like, what's the story? We had the lemma that says QCMA generates a sampler. That one's really kind of generic.
Yeah.
Right? It's like a generic transformation of a QCMA to a sampler. But then the whole second part was to create what is the right sampling problem where I also can marry it with the corresponding upper bound. So you sort of work backwards. You create a problem where you can actually construct the upper bound, and then you marry the distribution and stuff to fit it. Right? That kind of makes sense.
I guess also maybe looking ahead a bit, like some of the power of the purification technique is you take a distribution, you turn it into a quantum state, and then you change the basis of that quantum state to do something cool with it, right? And that's like somehow if your distribution shifts a little bit, like then you change basis, it may look very ugly or something.
But the purpose of that is that then it allows you to compute things about these probabilistic experiments using the quantum technology. Yeah.
Let's see what the purification of a random multiset is. So I think I'm going to answer your question, but if not, I'll get to you. Okay. So we have these annihilation, these creation operators. And these are what we sometimes call the position annihilation and creation operators. And they actually have this kind of now here I'll write out what the coefficients are. So if you annihilate in a bin with LX bosons in, there's a square root of LX factor that comes out here, and then now the bosons drop. This has to be necessary because what happened if you annihilated a situation where there wasn't a boson, right? You need to sort of throw an error, and so that would be square root of 0, and that's your error that's being thrown. You can always create a boson. You can always create one, even no matter how many are there, but you'll have this. And another reason why you'll need these normalizations is because these bosons they're representing these multisets, but order independent. So these coefficients that are being knocked out are doing all that combinatorial quantities of like remembering, the labeled or ordered versus unordered sets, all that, is kind of being handled by the boson situation. Okay. Consequently, you can just put these two together and you can get the number of bosons, and this has a name, it's called the number operator. Okay. Now let's get into something interesting. As Anand suggested, the whole point of this is we want to look at this purification in another basis. And the basis we're going to look at is called the momentum basis. And these names come from physics. So what we've talked about so far are the position clock basis and position annihilation and creation operators. Okay, next we'll define what are the momentum analogs. And here I'm going to use a computer scientist's definition of momentum. And the way you define the momentum analog is you take those creation and moment and annihilation operators. A for annihilation, by the way, and A dagger is the creation. It's the anti. It's not annihilation, right? And what you do is we define them by applying the Hadamard transform. So to create a boson, this is the creation operator. To create a boson at a momentum y is like to create a superposition of bosons at different positions. Okay? Just technical definition. And this is what's really powerful. This is where you get the Heisenberg uncertainty principle. So let's just take this creation and let's focus on creating a boson at 0. Okay? Creating a boson at 0, this pesky phase goes away. And all you're left with is that the creation of a boson at momentum 0 is a uniform superposition of creating it at every position. Right? So another way of saying this is if you let the vacuum state be the state with no bosons in it at all, then the purification of just tossing one ball into a random bin is just one boson at momentum 0. Like, purification, it's not the only purification, but it's a really nice one. Is one boson at momentum 0. It just sits there, all by itself. And this matches our notion of Heisenberg principle, which is if the position is maximally uncertain, then the momentum is certain, right? And that's what we have here. So sampling a uniformly random boson, one of them, momentum 0. Here's the nice part. Purification of a random multiset is just L bosons in 0. This is create L bosons in the 0 momentum mode. This is a normalization. Don't worry about it. This is what it is. How do you do it? Expand it out. Look, it's just now the linear combination of all possible creations. And it's also keeping track of all the double counting, whatnot. I don't have to worry about any of that. And that's sort of your situation. So by picking the multiset, it had this really beautiful interpretation, which is that it's just in the momentum basis, it's just all the bosons are in momentum 0. So analogous to the position clock basis, you can have a momentum clock basis, which looks something like this. And now when you apply the momentum creation and annihilation operators, it just deletes the boson. These are just the bases, they're bases, they're, can apply the isomorphism, whatever. They're sort of the same. But what's the key point is my starting state. Oops, sorry. No, whatever. Yeah. My starting state is going to be L bosons in momentum 0. Right? If I just was focusing on purifying S. So what I can do is, if I had my situation of this nature, where, here was S and U, and I was looking at this, and now I can think of this as a boson position Fock state. So my S was the choice of multiset, but I'm going to replace it by thinking about the boson position Fock state. And what this is going to do is it's going to let me do something wild, which is here, instead of measuring to see if this was at S, I claim I can do the following thing. Okay? I can flip these to be controlled annihilations kicking back that way. So it's like when you get to this situation, you guess. I guess 0.7. I'm like, I'm going to drop my pin at the location 7. Like, if all I wanted was the norm of some number, it's like me applying the annihilation at that particular bin. Okay. Yeah.
A half the same as H, like the operator, or?
No, this is a position annihilation. So my annihilation is a position. Okay. Because just choice. I just chose to think of my purification in the position basis. And so my annihilation here are in the position basis. The fact that you can do this is actually can be expressed as Markov's inequality. And if that's one way, it's like replacing the probability with an expectation. Okay. I won't go into that right now. The point of this, though, is that now let's look at the easy case, the 0 query case. So imagine I had an algorithm which had made no queries to you. Surely you can't guess, right? It's like an Arthur who doesn't even look at you, just drops pins.
Wait, sorry, it's like saying that, like, sort of, if someone produces a guess as, like, if that bin was empty, you should just, like, delete the whole state because you failed. And if that bin was not empty, you just take one of the balls out and you're like, guess again.
Exactly. Because
And that's the effect of like annihilating.
Exactly. Yeah.
Because if you guessed a bin which had no boson in it, let's remember that the number of bosons is like it's like 2 to the n over 10, and there's like 2 to the n bins, right? So basically all bins are empty. So if you just guess a random bin, you're going to annihilate a boson that doesn't exist, and you're going to fail. Okay. So this is exactly what happens. Let's consider the 0 query case. No queries are made to you. I should be able to prove this. And I know what my guessing probability is. It should be like the size of S, which is L, over 2 to the n to the v. Okay, which is, some exponentially small thing, blah, blah, blah. Why is that the case? Just random guessing, the chance I get the guess right is is L over 2 to the n. And I have to make v many guesses. This is my bound. This is what I'll get. Okay, can I prove this bosonically? And indeed I can. Here's what I'll do, is I'll say the guesses were at locations Z1 through V, and then the success probability by bosonic interpretation is that this probability of successfully annihilating bosons at the corresponding locations, starting from a state of all the bosons in the 0 momentum mode. You can write it this way. This is the number. It's like apply the annihilations. These are the hats. By the way, the hats refer to position operators. Tilde, they're momentum operators. This is just the physics convention. So I create a bunch of bosons in 0 momentum, and I start to destroy, but I destroy in the position basis. Okay. And you can prove this just by Heisenberg uncertainty principle. Each annihilation of a boson is very unlikely to occur because the bosons are in this like uniform superposition. They're like everywhere, right? They're everywhere, which means they're also nowhere, right? So if I drop a particular annihilation, it's very unlikely, and I'll get this kind of bound. So I can prove this by boson if I really wanted. Yeah.
And also, like, I guess Heisenberg uncertainty is like the intuition, but also there's just like a very nice like commutation relation of the operators. So you can do it by rote algebra.
You could rote algebra this exact state.
Easy rote algebra.
Okay. Easy for some.
I mean, like, you don't have to think. Like, you just like, I don't know.
Okay. Yeah, you totally can, right? This fact is. Yeah. Okay. What do you do now? Now we have to do this where you have to make queries. Okay. And this is where it gets ugly. But here's the idea. The rough idea is I'm going to do the following. Is I'm going to define a set of states that captures all the bosons in 0 momentum, but not exactly. It's like a slightly bigger generalization. And that's going to be a set of states called quasi-even condensates. Okay, this is the name I kind of made up using some names that are actually known in physics. And what I'll do is I'll prove that the post-query state is like really, really close to this space of quasi-even condensates. Okay, and once I do that, I'll have to do two things. I'll prove my probability bound for the quasi-even condensate, and then gentle measurement with this small distance is good enough, right? That's what I'll get. Okay, and the all bosons in zero is a quasi-even condensate. Okay, so what is this quasi-even condensate? Let's start off with the phrase condensate. It's a word from physics. It's actually just any state where basically all the bosons are in the zero momentum mode. So I'll define an R condensate to be any situation where most of the bosons, only R of them have drifted away. Almost all the bosons are still sitting in the zero momentum mode, right? And this is like kind of suggesting my intuition. I start off with all the bosons in zero momentum, and I show that as I make queries, the number of bosons that are going to drift away from it is really small. As long as I can bound and say that not too many bosons have drifted away, I'm happy, I can prove my theorem. Almost, I'll have to define one other notion, which is just quasi-even. A quasi-even is just says how many modes have an odd number of bosons. You ignore the zero mode. That one's special. So how many of the ones other than that one have an odd number, and I'll call it O. Okay? And what I'll show is that like as long as you know the number of modes which are odd is very small, and that the state is a condensate, I can prove my theorem. And I'll just say something is an RO quasi-even condensate if it puts the two categories together. So it's like almost all the bosons are there, most modes have an even number.
But don't you expect like the nothing is drift away? Kind of?
Mm.
Why? Because it's so sparse. So when you
Yeah, so great. I wish that was the case, that nothing would drift away. But every time I look at U, because U is spectrally correlated with S, I do start to learn something about S, right? Like the general idea is imagine I got to learn all of U, right? I looked at all of U, I would actually have a
relation.
because they're correlated.
Okay.
But the thing is, U, like here's all the points, everything kind of coming together. U is in the momentum basis of S, right? Like if S is the positions, U is like some understanding of the momentum. So it makes sense that querying U as an operation is a momentum operation. It like has a behavior that's understood in the momentum picture. But if I get to learn enough about all the momentums of the bosons, then I actually can know all their positions. That's the unfortunate thing. Okay, so how am I going to prove this? Is the initial state is a quasi-even condensate. It's a 0, 0 quasi-even condensate, this state. And here's what I'll do. I'll prove that after T queries, you're very close to being a condensate. You're iota close to a condensate that depends on this. This is actually saying that there's a family of condensates for every choice of iota. And I'm just sort of doing tail bounds, right? This is saying what mass of the state has actually drifted away, and it scales, right? But as long as the number of queries is small, and I want a really good bound, I actually can do just fine. Like I can say how many bosons have drifted away, and this is fine. Second thing, I'll say that the probability after T queries that you've generated a lot of odd bosons, like say V over 4 of them, is bounded. You can also bound it's exponentially small. Okay, it's very unlikely after T queries that you would have generated a lot of odd bosons. Okay, and the last thing I'll do before I release everyone, and we can then go into the more serious part. Sorry, I'm a little over time. Looks like everyone's still entertained enough. Is to say what the queries do. Okay, I'm going to lie. I'm going to lie to you, and I'm going to say that every time you query at Y, the action on S, because you query at Y, whether it's a member of U or not, but that has a kind of a kickback action to what's going on in S. I'm going to claim that the query is actually given by this very particular operator, which is called the double hopping operator, the double hopping momentum operator. I'll describe it in detail. I'll draw pictures and stuff. Okay, but let me just claim that this is the case. Okay. And where does this come from? It comes from the fact that I included Y and U with this kind of probability. Taylor expansion tells me it's like this, okay? And what you can show is that this, if I looked at the operator which kicked off, which multiplied by these coefficients gamma in uh in the position basis. This is like a position. This is the position side of the equation. This is the momentum side. I'm writing the action, which is a position action, also as a momentum. This is just for intuition purposes, that like there's some reason to believe that since I'm including things with probability like proportional to gamma, that they should have a behavior in this way. And you can prove this statement. It's pretty easy. I think it's like 5-6 lines, but that this is both the position and the momentum view on the same transformation. Okay, so what is this double hopping operator? Here's what the double hopping operator is. Let's look at it. It says for any x prime, annihilate bosons at x and x prime, create bosons at x plus y, x prime plus y. So pictorially, what happens when x equals x prime equals 0, right? Okay, you write out this component of the term, and let's say we are in a situation where we're like already a condensate, we're like L minus 5 bosons here. Now, 2 bosons get deleted from 0, and 2 more bosons get created at 3, right? Just because let's say I'm looking at H3, this is one term of that thing. The important thing to remember, though, is that these annihilation creation operators, they're not normalized, they're not unitary. So there's a normalization that comes out here, and it's roughly going to be it's going to be based on the number of bosons at the sites where it was applied. So originally there were 5 L minus 5 here, so that's where the L minus 5 comes. Now there's L minus 6, that's where the L minus 6 comes. And these numbers here, 1 and 1, are coming from the creation. Actually, that should be a 2, whatever. But what's the point? The point is that this number with the normalization is basically 1. Okay? Let's consider another term that occurs in this double momentum hopping operator. Let's consider it when x equals 0, but x prime equals 1. Okay? Now, the hop looks like this. One boson shows up here. One boson shows up here because I'd hopped one of these bosons also. But the normalization is way, way smaller. It's order 1 over root L. So what that tells you is even though I apply the hopping operator, if I start from a condensate, like this is sort of the punchline, so if I start from a condensate, the action of the hopping operator just moves those bosons from that location to Y. If it truly did exactly that, then for those of you who are worried, this would be a completely recording oracle. It would be recording the queries to Y. Fortunately, it's not exactly that, but that's a great intuition to get started.
Let's say that again. So
imagine that this number was so small, it was basically 0, and that actually will be the case as L goes to infinity. Then the action of applying this hopping operator literally would just move 2 bosons from the 0 to location Y and do nothing else, right? Like in the limit. As the number of bosons goes to infinity in the limit, that's exactly what that.
none of the other operations would actually happen because they're
Yes.
just vanishing.
Yeah, because comparatively, the action of the hopping operator would be ridiculously small. So that's really nice.
What's this recording thing? What the?
Oh, because now that says if I look at this S oracle and I look at it in the momentum basis, it is written out where the queries were happening. Because if I queried at Y, now there would have to be 2 bosons at Y, right? And I queried at Y prime, there would be 2 more bosons at Y prime, et cetera, et cetera. So if I looked at this momentum picture, I would have you could have read back all the queries the algorithm made. So you run the algorithm and I.
Oh, I see.
Right? So it's kind of incredible. It kind of writes down the queries exactly.
It also checks out that it doesn't work for 0, but also there's no reason to query 0 because that just tells you the size of the set.
Mm-hmm. Yeah. So the big punchline is that the operation of this hopping operator, it's really only affects starting from bosons at 0. And secondly, it's going to hop 2 bosons together, right? Because if you start them both at 0, they're both going to end up at Y. And so the probability that they are start to drift apart, right, that you get these weird non-even excitations, is basically really small. So you put all this together and you get the following theorem. That as long as I start off with a quasi-even condensate, one operation of the hopping operator gives me a condensate with just 2 more bosons lost. Fine, doesn't seem that bad. And the probability that it's not quasi-even, it's like I've increased the oddness of it, is very, very small. Okay. Last things, we'll just end here in a second. Then by induction, T applications, would be good. And what you can do is, as long as you can prove a statement like this, that if I start off with a quasi-even condensate, I have a nice exponentially small bound, I would be good. And that would prove the theorem. Okay.
Sorry, but I'm confused. So, I mean, that was a statement about the double hopping operator.
Yeah.
But now I've got, generally T of n queries or something. So how do I translate the general queries to like implementing double hopping?
So in this abridged section of the talk, I'm going to ask you to believe that every time I make a query, it only applies to hopping operator.
Oh, okay.
In reality, it's way more often than if that was the case, the picture is nice and we'd all be happy and we'd be done. But that is not the case, and it's a little bit more complicated. Okay, this is where I have the hyperlink. Running out of time. Okay, so this would get us to like this kind of theorem. And what are the lessons to take out of this? Well, it says QCMA algorithms cannot calculate spectral correlation to even constant accuracy with the sets S and U. I think the most accurate, the most helpful lesson you should take out of this is that if is based on this result of Henry Ma and Anand Natarajan, here at MIT, which is that QMA can also be reformulated in terms of spectral correlation, except when S and U are these solution sets to some CSPs. Okay, and therefore, if you were to prove QCMA equals QMA, that would mean that whatever QCMA algorithm you have for solving the QMA problem, it cannot just look at the sets S and U generically. It has to be based on the structure of those CSPs. Because if it looked at them in a black box manner, your algorithm could have been framed as the spectral correlation black box problem, which I just proved to you is impossible. So therefore, the QCMA algorithm would have to really depend. This is the analog of how the search oracle that separates BQP and NP proves to you not that there is no BQP algorithm for NP complete problems. That's not what it says. It just says if there was a BQP algorithm for NP complete problems, it would have to depend on the structure of whatever SAT formula you were trying to solve. So this is the QCMA QMA analog of this very nice original oracle separation.
Do people believe QCMA equals QMA? Okay.
But people don't believe BQP equals NP.
I agree.
Yeah. So, but what is the actual lesson you can take away from it? It just says that all the oracle separations do is they tell you that if you were able to solve it, the algorithm has to be structurally dependent on the CSPs.
Sure.
And since Anand and Henry just proved that QMA is really characterized by these two CSPs, one in the standard and one in the Hadamard basis, this result married with theirs says that if QCMA equaled QMA, it would have to depend on the structure of the CSPs. It's perfect completeness QMA.
Oh,
yeah. Okay, nice open questions about there are lots of other problems that have used quantum oracles both in cryptography and just in complexity theory. Can you replace them? Given spectral correlation's intimate relationship with QMA complete problems, what's the best algorithm for it? Are there any insights on errands and unbiased? That's a nice open question, and I think I'll end there. Yeah, thanks.
Okay, so we have